All right, so I tried to give you guys a pretty good rundown of the type of problems that you should expect. So hoping we get everything covered. So starting with 1 to 17, every other odd. The first one is one of these average rates of change problems. So just so we know, and I know a lot of us have trouble with this, it says exercise 1 through 4, refer to figure 1, in case you're wondering what you're supposed to be taking the average rate of change of. So the average rate of change over 0 to 2. Anytime that you read the phrase average rate of change, you should always think of the word slope. And by slope, I mean your classic like change in y over change in x. So change in the function over change in x. So to set up, we do f of 2 and then minus f of 0 and then over the change in x, which is 2 minus 0. So again, we've got a graph to look at, and so we're going to estimate exactly what these y values are when we look at the chart. So let me pop this graph in front of us here. So we are looking at, here it is, this picture. So f of 2, we just follow up the scale here, and that hits a y value of 7. And then f of 0 has a y value of 1. So again, just looking right at the picture here, f of 2 has a y value of 7, and f of 0 has a y value of 1. So we can plug those in. So f of 2 is 7, and then minus f of 0, which is 1, and then over, of course, 2 minus 0 is 2, so 7 minus 1 is 6 over 2, which is 3, and I don't think we have units here, do we? No, so normally you would have something like, meters per second or something like that, but I guess this is just 3. So our next one in order would be number 5. Number 5, we are computing f prime of a using the limit definition. So our function is f of x equals x squared minus x, and then the value that we're looking at is at a equals 1. So this is now going to feel super old school because you guys are so used to just being able to use the power rule and throw the 2 out front, and then the derivative of x is 1. But for this, we are going to practice using the limit definition. We only have 2 on the review, number 5 and number 9. And then number 13 kind of relates as well. But what we're doing is we've got this whole formula that we need to set up. So the limit as h approaches 0 of f of x plus h minus f of x, and then all of that over h. So this is where that 4-part definition of a derivative comes in, those 4 parts that I showed you. So part 1 is we find just this, simplify it up, subtract f of x, simplify it up. Every factor, or every term should have a factor of h. Then we divide and cancel out the h, and then step 4 is we take the limit as h approaches 0. So start with the first step, which is finding f of x plus h. So this one's going to require the most work because we're going into this function right here. Everywhere there's an x, we're replacing it with an x plus h. So quantity squared, and then minus x plus h. Make sure you have it in parentheses because we're subtracting, so you want to make sure you're subtracting the h as well. So this thing right here, we write it out twice, like x plus h times x plus h, and then we FOIL it. When we FOIL it, we get x squared, and then there's going to be a 2xh. Here's an xh, here's an xh, and then plus an h squared. And then minus x minus h, because we're subtracting this x, but then we're also subtracting the h. So right now we've got 5 different terms that are actually all completely their own variable parts. There's no combining that we can do right now. But step 2 is we take where we left off in step 1, and then we subtract the original function f of x, if we're following this formula right here. So then minus, in parentheses, x squared minus x. So we've got this x squared that can cancel with this x squared, and then this negative x, then we have minus a negative x, so those will cancel as well. So what we're left with is a 2xh plus h squared, and then minus h. So this, what I said about step 2, is we cannot go on to step 3 until every single term from step 2 has a factor of h in it. So 1, 2, 3 terms, all 3 of them have a factor of h. So we can move on to step 3, where we take our results from step 2, and we divide by h, simplify up, so we get a 2x plus h minus 1. So that is our derivative so far. The last thing is to take the limit as h approaches 0, that's step 4. And now, of course, at this point, algebraically, we're ready to just plug that h in. So we can just plug in h is 0 right here, and that leaves us with a 2x minus 1. So that is the derivative, which, like I said, if we just do the power rule, we move the 2 out front, we get 2x and then minus 1. We know that's the derivative. Obviously, I'm sure you're thinking, well, this is a lot faster. You do need to be able to do this for the AP test because this is where that formula comes from. We memorized the rules because we figured out once we did it enough times, like, oh, here's the pattern for the power rule, which is why now we can just go from here to here, but this is where it actually comes from, is all of this. All right, so finally, the last thing we're looking for is we want f prime at 1, because we're looking for a equals 1. So we plug that right into the derivative here. So 2 times 1, and then minus 1 equals, of course, 2 minus 1, which is 1. That's one option. The other thing you could have done is right from here, like instead of using an x, we could have put a 1 right here, and then we would have a 1 right here. So that's an option. We did it that way as well. I actually just realized as I was going through, like, oh, we probably could have done that. But either way works. You can use an x, and then when you're done, you can plug in the 1, or you could have had the 1, you know, here, 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 everywhere there was an x. Either way will work. You will come up with an answer of 1 when you're done, no matter what. Okay, number 9 is another limit definition. This one we are actually looking for the derivative. So the y value is the y function is 4 minus x squared. So we're going to do that exact same 4-step process. So step 1 is we're going to do f of x plus h. So we have 4 minus, and then we plug in an x plus h right here, quantity squared. Be careful here because I'm subtracting that entire quantity. And I just talked about how we FOIL this out. X plus h times x plus h. So that is our factor right here. Let's write it one more with everything actually subtracted. So there we go. So that's step 1. Step 2 is we take what we just left off with, and then we subtract the original function. So we subtract the function 4 minus x squared, and of course, just like last time, now everything should have a factor of x. So the 4 minus x squared cancels with the 4 minus x squared that we subtract, and it leaves us with this right here. 2 different terms, both of them have a factor of h, so I can move on to the next step. So what I get is a negative 2x minus h. And then finally, I move into my last step where I take the limit as h approaches 0. So I take the limit as h approaches 0 of negative 2x minus h, and I just plug in the 0 right here for h, and I am left with a negative 2x. So that's my derivative, which again, if we had just looked at the function and done a very quick power rule, we would have gotten a derivative of negative 2x, but it explicitly said using the limit definition. So on your test, it will say to use the limit definition of a derivative, and that's how you'll know that you can't just use the quick tricks. But in the interest of time, do not do the limit definition unless you're explicitly told to do so, because that would take way too long. Okay, last one with the limit definition anyways. Okay, so this is supposed to be in this form. So we're supposed to be expressing it as a limit. So let me write this out. So I'm using a here instead of x just because it's clear that they've actually plugged in a value. So our goal is we're supposed to find what function they're taking the derivative of and at what value they're taking the derivative. So this piece right here, this is supposed to be the function with an a plus h plugged in. So it seems pretty clear that the a that they're plugging in is a 1. So we know that. We know that the a is 1, and the function that they're plugging 1 into appears to be the square root of x. Okay, so if we were to take this function, f of 1 plus h, you would plug a 1 plus h into the square root, and then minus the square root of 1, which is 1, and then over h. So based on this as our generic formula, knowing that the limit looks like this, we can tell that this is the function they're taking the derivative of, this is the point they're taking the derivative at, so we can express the limit as a derivative. I would say if this is a function, what we're looking for is f prime of 1. All right, so now normally that would appear on the AP test as like a multiple choice question. You wouldn't actually have to find the derivative. You just have to pick out like, oh, this is the function they're looking for, and this is the point where they want the numerical derivative. All right, find f of 4 and f prime of 4. If the tangent line has the equation y equals 3x minus 14. Okay, so the graph of f of x at x equals 4 has this as a tangent line. Okay, so here's what we're trying to figure out. We know what the tangent line is. We want to know what the derivative is, and we want to know what the original function is where they meet the point. So let's get just a quick sketch. So first of all, we know that the derivative has this slope right here. We know that. So that one's pretty easy to pick out. So it must be the f prime of 4 is 3. So we can pull that right from the derivative. So what's happening here, and I know this one's a little bit tricky, is they give you the derivative. They give you the tangent line, but they don't give you the original function. They don't give you the derivative. So anything linear like this, whatever the slope of the linear function is, that's the slope of our function at a specific point. So at this particular point, x equals 4, our function has the same derivative as this tangent line. And derivative just means slope. And so if you guys were in Algebra 1 and I asked you what the slope of this line was, you could tell me that it was a slope of 3. All right, so we've got that going for us. So slope is 3. Now what you do is we're saying, all right, if we plug 4 into this function and we plug 4 into this function, f of x, they're supposed to have the same y value. Because if you picture like any tangent line, now I'm not saying our thing is quadratic, but let's say we've got a tangent line like right here. So we know that not only do these points have the same slope, this point they have the same y value. So here, the tangent line has the same y value as the original function. So if we know what f of 4 is in the tangent line, we know what f of 4 is in the original function. So y equals 3. If I plug in a 4 right here, what I end up with is a negative 2. So that means that f of 4 must also be a negative 2 because the linear function and our original function share the same y value and the same slope. All right, so that's number 17. Number 18, we've got these derivatives. So I'm going to take a look at the graphs right here so you guys can see these. So each figure shows the graph of a function and the graph of its derivative. We want to determine which is the function and which is the derivative. So starting in graph number 1 here, this one should be fairly obvious. A is something quadratic, B is something linear. We know that a quadratic function always has a linear derivative. So here A is the original function and then B is the derivative. When we're looking here at A versus B, A looks like it's quadratic or it could be trig. It actually looks like it's a piece of a cosine function. And then B looks like it's a piece of a sine function. So the derivative of sine is cosine. So that must mean that B is the original because that looks like a sine graph. So A must be the derivative because that's a cosine graph. We can go off of that, just kind of knowing patterns. Or we could look at a couple of specific things. So if we say that B is the original function, for example, B is increasing from this point to this point, and A is positive from that same x value to the second x value. Remember, anytime your function is increasing, your original function is going to be positive. So my original function, B, it's decreasing until this x value, increasing until this x value, and then decreasing thereafter. Whereas A is negative until this x value, positive until this x value, and negative thereafter. So the increasing, decreasing parts of B match up with the positive and negative parts of A. So again, B is the original, A is the derivative for Roman numeral number 2. And for Roman numeral 3, we've got A is a quadratic function and B appears to be a cubic. So again, just going by patterns, the cubic must be the original and the quadratic must be the derivative. But let's look at some patterns too. So B is increasing until about here. And you'll notice that A is positive until that same x value. And then it's decreasing until here. And again, you'll notice A is negative until that same x value. And then it's increasing thereafter, and A is positive thereafter. So those are the things that you're looking for. So in this one, B is the original and A is the derivative. 19, we've got some more pictures here to look at. It wants to know if A, B, or C is the graph of the derivative. Now for this one, we can't just use our nice little rules that we had, because, like I said, in Roman numeral 1 and Roman numeral 2, we basically just use, in Roman numeral 3, 1 and 3, we just use power rules that said like, oh, the derivative of cubic is quadratic, the derivative of quadratic is linear, the derivative of linear is constant, etc. For this one, you've got some sort of crazy function. So what we're going to look at is where is the red function increasing and decreasing versus where those blue graphs are positive and negative. So, for example, let's look at f of x, let's find where it has high points and low points, because that's where this graph should have zeros. So somewhere in between -2 and -1, my derivative would cross through the x-axis. So it happens here, it happens here, it happens here. Okay, so they're all still in. And then right here, again, between -1 and 0, we should cross through the x-axis. It happens again here, but barely. It doesn't happen here. Okay, so B must be out. And then it happens again here in C. So again, what I was looking for there, this graph had a slope of 0, right around negative 0.5. So this one's out because it did not cross through the x-axis here. This one looks like a better candidate because it looks like it's crossing through the x-axis at the right moment, but I guess this one is possibly still in. And then this one has another peak at about positive 0.5. So again, our derivative should cross through the x-axis here. So A, again, that one looks a little iffy because it looks like it's way too close to 1 that it's crossing through the x-axis. This one looks good. Looks like it's crossing through at about 0.5. All right, so one more thing I want to point out about A, just to show you why it's not right at all. See how A is crossing through the x-axis right at 0? That should mean that the original would have a high point or low point when x equals 0, and this one doesn't. So again, A is out, C is in. Let's just compare exactly why. So C is positive here, here, and here. So to the left of negative 1.5, in between negative 1/2 and positive 1/2, and then after about 1.5, or these might be like 1.25. Whoops. So again, this is increasing here. That's where my derivative was positive. Increasing here and increasing here. Those are all the places my derivative was positive. And then it's negative in this little piece, which is when my original graph is decreasing, and it's negative in this little piece, which is where my original graph was decreasing. So we're always looking for those increasing, decreasing features versus positive and negative features on the derivative. All right, so we're going with C for number 19. All right, now we are off of the graphs, so we can go back to our page here. Okay, so our next problem is number 23. Okay, so number 23, again, it says exercises 23 and 24, use the table of values. So what is the interpretation of A prime of t? So this one's a little weird. Hopefully we did okay with it. But the AP test loves when you interpret what the derivatives mean. So A is the number of automobiles manufactured in the United States. So let me just write something on here. So A of t equals the number of automobiles manufactured. Okay, so what this means, A prime represents a derivative, and a derivative is a rate of change. So A prime of t is the rate of change of the number of automobiles manufactured. With respect to time. So basically, the number that they're producing each year, is that number increasing? Is it decreasing? What's happening as time goes on? That's what A prime of t represents. And then it says represent A prime of 1971. So we wanted to know about how the number of autos is changing in 1971. So they give us values in 1970, in 1971, and 1972. So what I would do is I would go from 1972 back to 1970. So it's approximately, we want to know the number in 1972, and we want to know the number in 1970, and then divided by a 2-year lapse in time. We don't want to go from 1970 to 1971 or from 1971 to 1972. We want to actually get a little bit on both sides. That way we can see what happened the year before 1971 and then what happens, I guess, kind of after 1971. All right, so we get a nice little lapse here. So 1972 is 8.83, and that is in millions. And then minus the number 1970, and that is 6.55. That is again in millions. And then divided by a rate of change of 2. All right, so this we divide out, subtract here. I've got 8.83 minus 6.55. All right, so that is 2.28 million. When I divide that by 2, I get 1.14. So that again is in millions. So this is in millions of cars per year. That's the rate of change. Okay, so number 24 is also related to that same chart. So it says, given the data, and then we've got some graphs below, so I'll put those on the camera too. Which of A through C could be the graph of the derivative? So I want to get that chart in front of us. There we go. Okay, so you can see some different things. When we're looking at a derivative, we want to know whether the values are increasing, decreasing, kind of staying the same. There's some different features that we can look at. Like A has a pretty sharp increase, then it kind of levels out almost, then a decrease. C, we've got this really serious decrease in that graph. So if we look at some of these values, it appears that we're increasing, we're increasing, we're increasing, and then the decrease happens somewhere in here, but then it starts increasing again. So we're looking for a definite increase, and then a decrease, and then another increase. So part B definitely does not seem to be doing it, because you can see that these are decreasing between 1970 and 1971. That's just not happening. But we can see, if we look here, that's pretty steep, and then not so steep between 1970 and 1972. So I would say that A looks pretty good there, because you've got this steep increase, and then it's not so steep between between 1971 and 1972. But then again, this one right here, yeah, the decrease doesn't seem to happen. This one has the decrease happening between 1972 and 1973. That's not where the decrease happens here. So we're going to go with A for this one. You've got a pretty serious increase in between 1970 and 1972, which you can see on the table here, and then it doesn't increase quite as much between 72 and 73, and then you've got a decrease between 73, 74, 75, and then it kind of goes up again. That part doesn't really match. All right, let's look again at C. Okay, so here we've got a positive rate of change. Oh my goodness, I was explaining this all wrong. Let's try this again. These are derivatives, and so the derivative shouldn't be increasing. This is supposed to be the derivative. I'm sorry, not the actual function. Ignore everything I just said for the last 2 minutes. Okay, so we need these values to be positive because we are increasing. Okay, so here, from 1970 to 1971, we want it to be a positive value. And so a positive value would be one of these. Here, the negative A prime says that your function would be decreasing there. So A is out. So we're between B and C. What happens here is that here between 1972 and 1973, it has a decrease because it's got a negative slope. So that doesn't appear to be true. But then C also has a negative slope. So if we're looking between 72 and 73 here, it looks like it increases. You know what? It could start decreasing between 1973 and 1974. So I am going to look at B. I like B, because what happens here is, see how right here we start increasing again, and this is when it gets back above the x-axis. So there appears to be increasing happening as far as 1973. Could happen somewhere in this range where the decreasing would start, and so your derivative is positive here, and then when the derivative goes below the x-axis, that is when the decrease happens throughout here, and then it pops back above the x-axis, and that is where we've got some increasing. So I'm sorry, I was mixing those up. I thought this is supposed to be A. But again, A prime, we're looking for what's above the x-axis and what's below the x-axis, so that is going to be letter B. Next one, we are doing all of 29 through 34. All right, so let's just switch this to a 29. All right, so these are just pretty basic derivatives. Now again, unless it tells you to do the limit definition of a derivative, you are going to do just the power rules, everything that we learned for the last couple weeks. Okay, so this one we've got just a couple power rules to do. So y prime, first of all, we do the power rule here. The 5 comes out front, multiplies by the 3, we get 15, and then the power drops down 1 to a power of 4. Minus, with this one the 2 comes out front, multiplies by the 7. Power drops down to a 1, but we never write x to the first. And then the derivative of 4 is just 0. So this is your derivative right here. 30, we've got y equals 4x to the negative 3 halves. So same thing with the power rule. Here, the negative 3 halves is going to come out front, multiply by the 4. So negative 3 halves times 4 gives us a negative 6. And the power drops down to a negative 5 halves. So that's your derivative there. 31, I have something very similar, t to the negative 7.3. So they're just throwing in a decimal just to show you that the power rule works no matter what. So the negative 7.3 comes out front as our new coefficient, and then I subtract 1 from the old power, so now my power is a negative 8.3. Let's sneak some more in this blank spot here. 32. Okay, another power rule here. So I've got 4x squared and then minus x to the negative second. So y prime, just a little power rule here. The 2 comes out front, multiplies by the 4, so I get 8x. And then minus here, the negative 2 comes out front, so I end up with plus 2x, and the power drops down to a negative 3. 33, here's my first quotient rule. So I have an x plus 1 in the numerator over an x squared plus 1 in the denominator. So you might be thinking you can do some factoring and canceling. You can't, because x squared plus 1 does not factor. So I can set up high is an x plus 1. D high ends up just being a 1, because this is just a linear function here. Low is x squared plus 1. And d low is a 2x, the derivative of this using a power rule. So y prime, my quotient rule is low d high, so I multiply these two together. So low d high is just an x squared plus 1, and then minus high d low, so minus an x plus 1 times the quantity 2x, and then all of that over low, so x squared plus 1, quantity squared. Now the denominator, you do not need to FOIL that out. We are going to do some distributing here, so distribute the 2x, and I have the quantity 2x squared plus 2x. So I can do some subtracting, so x squared minus 2x squared is a negative x squared, and then I have minus 2x, and then here's the plus 1 from the left-hand side, and then over the quantity x squared plus 1 quantity squared. And that's as far as you need to take that. Like I said, no need to FOIL out the denominator or anything like that. Okay, and 34, I believe another quotient rule. Yep. Y equals okay, so we've got, again, high is a 3t minus 2. D high, since that's just a linear function, the derivative is just 3. And then our lower function is a 4t minus 9, and again, that's just a linear function, so your derivative is a 4, just like the slope, like in Algebra 1. Okay, so set up my derivative. Y prime equals low d high, so I can actually just distribute that 3, and I get a 12t minus 27, and then minus high d low, again, just distribute the 4, and I get a 12t minus 8, and then all of that over low, so the quantity 4t minus 9 quantity squared. So simplify this up. The 12 t's actually end up canceling. And then I have a negative 27 minus negative 8, so plus 8. So what I end up with is a negative 19, and then over the quantity 4t minus 9 squared. Okay, so next section, we are jumping all the way to 85. So all of these functions, if you look through, everything from 35 down to number 80, they all have what I call these nested functions, which is like one function plugged into another function. So notice like 35, for example, even the very next one. There's something to the 6th, and there's an x to the 4th minus 9x plugged in. Or like number 48. Looks like a run-of-the-mill sine function, but it's got a 4 over theta plugged in. And 62 is a natural log function, but it has an s squared plugged in instead of just an s. These are all things that we are not capable of taking the derivative of yet. So we are going to jump to number 85. Number 85, 86, and 87. We've got this table of values that we can look at. And so at once, so s of x is given as 3 f of x minus 2 times g of x. So the AP test loves to do these like generic derivative rules where you don't know what f of x is, you don't know what g of x is, but you actually don't need to in order to get everything right. So you're supposed to be taking the derivative of the given function. So s prime, for this function right here, we basically are just doing kind of a constant multiple rule. Like 3 is a constant, you just leave it out front, and then you take the derivative of this function. Now again, we don't know what f of x is, but we know that in generic notation, the derivative of f of x would just be f prime. And then minus, again, constant multiple rule says the 2 just stays out front, and the derivative of g of x is just g prime. So it's all done in generic notation, which is totally fine, because what they want is they're looking for the derivative. It said at x equals 2. So we want s prime of 2, which means everywhere we have an x, here and here, we replace it with a 2. Okay, so what we do now is we pull these values right off the table. So 3 times, and then if you look at that table right up above on the top left of 205, f prime of 2 is given as a negative 3, and then minus 2 times g prime of 2 is given as 9. So I simplify this up. 3 times negative 3 is negative 9, and then minus 18. So I get a negative 27 for number 85. So again, I don't know the derivatives. I don't know the original functions, and I don't need to. 86 is a product rule. So h of x is a generic product, a generic function f times a generic function g. I do not need to know what the functions are. So to find h prime, I set up my product rule. And the way that this works is I take the first function, which I can just write f of x, times the derivative of the second function, which again I'm just going to use a generic g prime, just represents the derivative, whatever it is, plus the derivative of the first function, a generic f prime, times the second function, which is g. So we're used to this formula with like u's and v's. This is u v prime plus u prime v. We can just plug in generic f and g. So again, we want the derivative at 2. So we just plug a 2 right into this notation, and we grab those values right off the table, just like we did with number 86. So f of 2 is 5 times g prime of 2 is 9, plus f prime of 2 is a negative 3, times g of 2, which is 4. So 5 times 9 is 45, and then minus 12, so I get a 33 for that second derivative. 87, I'm doing the same thing one more time. This time it's a quotient rule. So we are just practicing taking these generic derivatives here. So r prime, I'm going to do low, d high, so low is g of x, d high, I would write f prime, minus high, d low, I would again just write g prime, and then g of x quantity squared. Okay, so without writing it out again, I think I can just grab these values at 2. So g of 2 is 4, times f prime of 2 is a negative 3, minus f of 2 is 5, times g prime of 2 is 9, and then over g of x, quantity squared, g of x is 4, and then I square it. So 4 times negative 3, of course, is a negative 12, minus 45, and then all of that over 16, which is 4 squared. So negative 12, negative 45, I get a negative 57 over 16, which I don't believe reduces down at all, so we will just leave it like that. Okay, so just a couple more here. I'll get a clean sheet of paper for the next one. 91. 91, we want to find the points on the graph of, so let's write down f of x equals okay, so we want to find the points where the tangent line has a slope of 10. So these are great problems to practice when they give you a function like this, like number 91, 92, 93, where you want to find, where there's a horizontal tangent line, or where the tangent line has a certain slope, or where the tangent lines, 2 different graphs are parallel. Anything like 91, 92, and 93 are great examples to practice. So we want to find a slope of 10. So f prime represents the slope. We want the slope to equal 10. So of course we have to find the slope first using this function. So we find a function for the derivative. Just a quick power rule for all of these pieces. Derivative of x cubed is a 3x squared, minus the derivative of 3x squared is a 6x. The derivative of x is 1, and of course the derivative of 4 is 0. We want my derivative to equal 10. So I'm going to be solving for x. Since it's a quadratic, you should hopefully assume I will be finding 2 places where the derivative is 10. I start by subtracting 10 from both sides. So I get 3x squared minus 6x minus, 9 equals 0. So at this point, you might want to dive right into quadratic if you're not a fan of factoring. But one thing you can hopefully see is that I can factor out a 3 from all of these pieces, and then I can just divide it out. So picture dividing both sides by 3, and this is just gone. And of course, 0 divided by 3 is 0. Sorry. And then I've got x squared minus 2x minus 3. So this factors 2, and x minus 3, x plus 1. and that is set equal to 0. So when I set those both equal to 0, x minus 3 gives me a 3, x plus 1 gives me a negative 1. So let me just show you what that looks like on a graph. So if I plug that function into my calculator, supposedly at those two values I've got a slope of 10. So new graph page. So I can graph x cubed minus 3x squared plus x plus 4. This is not showing up very well. Okay, so there's my graph. So if we look at, let's get it to bold, there we go. So we've got at negative 1, which here's negative 1, looks like a pretty steep slope right there. Could be a slope of 10. And then again at 4, which is going to be something just beyond what we can see here, but again, it looks like the slope is getting steep and positive again. All right, so next one, we've got number 95, only two more left. 95, we want to take the second derivative. So the original function is 12x cubed minus 5x squared plus 3x. So you can't find the second derivative without, of course, finding the first derivative. So y prime equals 3 comes out front, multiplies by the 12, power drops down to 2, minus 2 comes out front, multiplies by the 5, power drops down to 1, and then the derivative of 3x, since it's linear, is just a 3. Then to get the second derivative, I take the derivative of that function. So again, 2 comes out front, multiplies by the 36, and then the derivative of 10x is just 10 because it's linear. Derivative of 3 is 0 because it's a constant, and so this would be my second derivative. Keep in mind that you might have to do a double product rule, maybe a double quotient rule, something with sign, maybe something a little bit more complicated than these. All right, and my last one, I've got another picture to look at, number 107. Okay, so label the graphs for both of these, f, f prime, and f double prime. So let's get those under here. So we have a red graph, a green graph, and a blue graph. So the first thing I want to point out, right here, this green graph, this looks like your typical absolute value graph. The derivative of this left-hand side is a negative 1. The derivative of this right-hand side is a positive 1. So this function, the green function, its derivative is definitely the blue function. So we've got that going. So we've got two options, really. Either green is f and blue is f prime, or green is f prime and blue is f double prime. We just need to figure out where the red one fits into all this. So this one, as I come up here, that kind of levels out right here. So it would make sense that my slope would be 0. So what we're trying to figure out is the green one the derivative of the red one, which would mean that red is f, green is f prime, blue is f double prime, or is it that green is f, blue is f prime, and then red would be f double prime? Well, we can cut that out immediately because f prime, this one, the blue one, these have just slopes of 0. So if blue were f prime, then f double prime would just be 0. So that means it has to be that red is the original function, green is the first derivative, and blue is the second derivative. Let's talk about why the red is the original function. See your function's increasing here, then it stops, and then it continues increasing. But as it's going here, it's slowing down. And what's happening is this green graph, its derivative supposedly is always positive, but the slope goes towards 0. The derivative heads towards 0, which is where the red graph is starting to level out. And then as it gets steeper again, that's where the green graph is increasing and gets a bigger slope. So the red one is the original, f, the green one is f prime, and the blue one is f double prime. Okay, so let's do the same thing over here with this one. We've got 3 graphs here. We've got the green, we've got the red, we've got the blue. I'm going to try to figure out which one's the original function. They all do very similar things, kind of off to the right-hand side here. The important thing I want you to look at is all of their behaviors in terms of like positive and negative, where it's increasing, where it's decreasing, things like that. So let's look at my green graph. My green graph has a peak right here, and it's got a peak right here. So I'm going to use a pencil so I can erase it. So this peak right here, and then it's got a peak right here. So if its derivative is present, its derivative would cross through the x-axis at that point. So notice, the red one does cross through the x-axis right there, and it does cross through the x-axis right here. So what I'm thinking is that red is the derivative of green. We'll test that out in just a second. That'll leave us to see with the blue one. So if red is the derivative of green, so what's happening before this pencil line? Well, the green one's increasing. That's where the red one's above the x-axis. Then the green one decreases. That's where the red one is below the x-axis. And then the green one increases again, and that's where the red one is above the x-axis. So I think we can be pretty confident in that red is definitely the derivative of green. So again, just like last time, we've got two options. Either green is f, and that would make red f prime, or green could be f prime, and that would make red f double prime. So it really all depends on where the blue one stands. So does it appear that the blue one is the derivative of the red one, or does it appear that the blue is the original function and green is the derivative of that? Since the blue one is kind of boring, I guess, it doesn't like loop up and down a lot, I would guess that the blue one is the derivative of the red one. So let's check it out. So the red one has this peak right here, kind of a low point. So let's erase these old lines so we can compare the red and the blue. Okay, so the red one goes down, has this low point right about here. Oh, and it looks like blue crosses through the axis here. So let's test this theory. Red decreases, stops, increases. That's the blue function is negative, 0, and then positive. So that tells us that blue is the derivative of red. So this is our order right here. All right, so that's the last one. Study hard and good luck.